lot of pressure.
No, no. Sure. And then they for watching it.
Or
For
it's
well, yeah, I guess.
To start, so I'm Philip Kim from Physics Department and want to introduce today's speaker, Dr. Luis Jauregui. Um, Luis got his the bachelor degree in 2007 in National University of Engineering in Lima, Peru. And then he came to US and studied in electrical engineering department in the Purdue University, worked with Yang Chen. And although he was in the electrical engineering, his main subject was more like kind of physics, and some of the really exciting work was done in the area of the topological insulator, where he just combined the magnetisms and superconductors together and look at the very interesting topological transport phenomena in there. And he got his PhD in 2016, and then moved to here at Harvard, working in my group already in 2015, right? So even before but he got the plan that he worked with us. It's been about 3.5 years he's working on this transition metal dichalcogenide heterostructures, searching for the excitons and exciton condensation. So probably we are going to hear about what he's up to.
Thanks, Philip, for the introduction, and thanks, Professor Rob, for the meeting.
So today I'm going to talk about these novel optical devices and on van der Waals heterostructures, and as Philip already mentioned, on TMDCs, or transition metal dichalcogenide. So this is the vision of what we see, how we see van der Waals heterostructures. It's a Lego blocks, all built up of different materials. Philip wants us to make some castles or some, I don't know if we can do that. But the building blocks for these Legos are different materials. They are insulators, semi-metals, superconductors, metallic, or also semiconductors. So today I'm mostly gonna focus on semiconductors and insulators, which are boron nitride per se. And there is magnificent things that it can be built up as in Lego blocks, right? So we can use graphene as interconnects, graphene inductors, or transistors like FETs, right? Or also tunneling transistors or biosensors out of these materials, and we can then at the end put them together, integrate them all together. Right, but let me explain a little bit more of each of these individual building blocks. As I said, graphene is one of those building blocks, and it's a semi-metal. It's a Dirac fermion at the end, right? There is no gap. Bilayer graphene has a tunable gap with electric field. We have hexagonal boron nitride, which has a large gap. It's an insulator. It's a good dielectric. It's a perfect dielectric, right? Layer by layer dielectric. We also have the semiconductor TMDCs, which have a visible gap. So we can use light to generate, we can couple them with light. So that's also the importance for these materials. And also, they have a strong spin-orbit coupling. They have this spin and valley locking that maybe I will mention later. And this is like the band diagram of each of these TMDCs. They have, as I said, the band gap is around 2 electron volts. The band alignment is very different between them. So we can choose, depending on where do we want the band alignment to start and what's the band gap that we need for each of these TMDCs. Okay. As I say, we can form these different type of heterostructures. It can be type 1 heterostructure, where we can put two elements of one of them of bigger gap than the other one, and the alignment is like a contained heterostructure. We can make a type 2, where they are shifted respect to each other, or we can make even a type 3, which is even more shifted. So with this, using these building blocks. So the first heterostructure that was made out of this, I will call it a type 1. Actually, it's a boron nitride with graphene. It was made in Philip Kim group in collaboration with James Hong and at Columbia, Anton Hans, right? So they were using boron nitride to pick up graphene, and at the end making these boron nitride, graphene, boron nitride heterostructures, and you can see they are atomically smooth. So it's not like you could think of made, since you're using tape to exfoliate each of these layers, it might be full of dirt in between, but they are actually atomically flat. There is no defects, or there is nothing trapped in between at this scale, right? And then, as I say, we are mostly going to focus on TMDCs. So for TMDCs, they are, as I say, they're semiconductors. They have a broken inversion symmetry that will be very useful later on. That in this talk, that I will mention how can we use them to identify edges on TMDCs. They have a gap of around around 2 electron volts, and also they have a spin splitting conduction band and valence band. So the spin splitting in the valence band is around 300 millieVs, and the spin is different between each valleys. So that's why they said about the valley and spin locking. And another important optical property from these TMDCs is like they are a truly 2-dimensional semiconductor. So there is a reduced dielectric screening, and you can create, if you shine light on them, you can create excitons, a truly 2-dimensional exciton, compared to gallium arsenide, which is really a 3-dimensional semiconductor, where as a point of comparison, the binding energy for an exciton in a TMDC is around 300 to 500 millieVs, compared to the binding energy of an exciton in gallium arsenide, which is only few millielectron volts. So that means you need to cool down gallium arsenide in order to see excitons, compared to TMDCs that you can see them at room temperature. Okay, but then the talk is about optoelectronic devices, right? So how can we make we need to make contacts first onto these semiconductor materials. So initially, they were making contacts on TMDCs, on MOS2 using graphene. So graphene, it was proved in this paper that graphene can make a good contact on TMDCs. They can, but this is only on like 6 layers of MOS2. They also show like in 1 layer in CVD and highly doped MOS2, they can also make good contacts. But it's not easy to make contacts on single layers. Why? Because of the gap. The gap changes with thicknesses. So the thinner it goes, in the single layer limit, the gap is larger. It's around 2 electron volts. And then there is another problem that I will mention here, the alignment. So we need to align this, either the conduction or the valence band to one of the metals. So this is some of the work function of metals. And we need to align them to either, as I say, to the conduction or the valence band. So it looks simple. So we can just choose a low work function metal and align it with MOS2, and then we will get a good contact. But in reality, it's not as simple, because once you deposit the metal onto a single layer material, what you end up doing is breaking bonds, and at the end, the metal will have a different work function on the interface. So what we have done here at CNS is we have characterized metal films. We have found out where is the work function. And instead of depositing the metal on top of the TMDC, we do it the other way around. So we deposit the metal first, and then we transfer the TMDC on top of the metal. So in that case, we eliminate this problem of the metal destroying the 3-atom thick semiconductor, right? And so we have characterized that for platinum is one of the largest work function and the one that works well for tungsten diselenide, for example, and that's part of the data I will show today. Scandium also works well for MOS2, but it has a problem. So all the low work function metals tend to oxidize very easily, compared to the noble metals, which don't oxidize, or if they oxidize, they form a metallic oxide. All right. So as I say, we lay down a TMDC on top of these pre-patterned electrodes, PT in this case, and we can get ohmic contact even down to single-layer tungsten selenide at low temperature. This is around 1.5 Kelvin, and we also test it in helium-3 temperature. So we can make ohmic contacts up to these low temperatures. What we have to do is also, if you notice here, there is a top gate. This top gate is in charge of doping the contact area as well. So it dopes the contact, and also it can control the channel doping. But we also have a bottom gate. So the bottom gate can take care of uncharging uncharging the channel length itself. But the top gate is very useful to dope these contact areas. So with this, we've been able to obtain gate dependence of Shubnikov-Dehaz oscillations. That's the first thing. So we apply a magnetic field, and then we form Landau levels, right? So, and then we can see these Shubnikov-Dehaz oscillations. We find this is a large doping. We can see a spin degeneracy of 2, because we have a spin up and a spin down, but in different values. And if we go to even lower carrier density, we can see now that this, instead of forming a G equal 2, now we have a G equal 1. So we have lifted the Landau level degeneracy, because we are in this situation. We are only probing one of the values in that case. But in Landau levels, right? So we can go to very low carrier density, to around 110 to the 12. Interestingly enough, even when we are reducing the carrier density, mobility is going up. So we are not seeing any charge impurity scattering dominated transport. That usually happens in MOS2. So for MOS2, you cannot go lower in density, because mobility really reduces a lot, as I will show in one of the slides. In tungsten selenide, on the other hand, the material is better, it's better quality, and mobility keeps increasing. There is a problem here. Sorry.
You know what? That is miraculous. I mean, why should it get better when you get closer to all the dirt on the traditional?
Right, but also I think the intervalley scattering might be reduced. So that's one of the. In tungsten selenide, we're mostly on the valence band. So in order to have intervalley scattering, we have to flip a spin. In comparison to MOS2, we have this, in the conduction band, they are mostly degenerate. So the spin flipping is possible. So that's one of the things that is reduced, the intervalley scattering. Yeah, that could be. Right. So we are not limited by this charge impurity, like in MOS2. And we also can obtain the effective mass, as it has been done also by others in the literature. We also obtain the effective mass by measuring the temperature dependence of the Shubnikov-Gas oscillations, and we obtain a fairly flat effective mass for a large range of carrier density. So it's around 0.33 the rest mass of the electrons. What happened with N-type? So all I mentioned is mostly for P-type. As I said, we are using these noble metals. We're placing the TMDC on top of the metals. What if we want to use, what if we want to make contacts on N-type materials like MOS2 or MOSE2? So in that case, there is a theory paper where they claim like if you introduce boron nitride to cobalt or nickel, the work function at the end reduces. And it's all because of the interface. Boron nitride is a dipole, it's a dipolar insulator, right? It's two different materials, boron and nitride. And either at the end, if you have a boron nitride in between cobalt and the TMDC, you end up reducing the work function. And here at CNS, we measure the work function of cobalt and boron nitride, and it's actually indeed reduced. So we obtain a work function of around 3.6 electron volts. So it matches well with MOS2 conduction band. And in MOS2, in single layer MOS2, we were able to also obtain Shubnikov-Gas oscillations at low temperature. But as I say, they are mostly limited by charge impurity scattering. Once we reduce the carrier density, mobility also goes down. So it's hard to reach into a lower carrier density dominated transport in MOS2. But we can get good contacts out of it. All right. Because of the good contacts, Ke-Wan in our group, he was able also to use graphene, as I mentioned, for multiple layers to make quantum dots. And I'm just gonna put this slide and probably then just to mention that we can have contacts and we can create these quantum dots on TMDCs, right? So Ke-Wan showed like he can get Coulomb blockade on 3 layers of MOS2 with these graphene contacts. I don't know if Ke is around, but he could explain it better if he's around. I will show later why is that important. So as I say, in these TMDC semiconductors, we shine light. We can create an electron-hole pair, which are bound by Coulomb interaction. We can observe once they recombine, once this, we are knocking out an electron from the conduction band, it goes to the valence, from the valence band, sorry, it goes to the conduction band, and then they form this exciton, this electron-hole pair, right? And they live usually short because they are in the same, they are aligning momentum, so usually they live like few picoseconds at most. And that's what they are called, like the direct excitons. And if we separate them in space, so if we have 2 layers separated by an insulator in between, we can have electrons and holes in different layers, and that is what is called an indirect or interlayer exciton. And the advantage of having an interlayer exciton is the lifetime is dramatically increased because now the wave function is separated by an insulator, and that's what it has been proved for gallium arsenide. And since the wave function, since now the lifetime of this, the recombination process now is longer because of the insulator in between, they are able even to prove spontaneous coherence or Bose-Einstein condensates in gallium arsenide, but this is all at very low temperature. Right, so excitons in 2D materials, I'm just talking about the single layer, right? Single layer excitons. No, I'm just talking about the direct excitons in TMDCs. Because of the strong confinement, they have a large binding energy. They have a spin polarized band, and they also are spin valley locked in just a single layer of TMDC, right? So these are some examples of what people have been doing with bi-excitons in MOS, in tungstenized selenide, or even what they have been trying to do with interlayer excitons in also TMDCs.
What is the binding energy of the exciton, and what's the spatial dimension?
So for a single layer material, the binding energy is around 300 millielectron volts, and the Bohr radius is a couple of nanometers. Okay, so we also can now look at the electro-optical properties of a single layer. So we have now placed this is tungstenized selenide in between boron nitride. This is a heterostructure of boron nitride. We have top and bottom gates. We can control the amount of carriers in the channel, right? As I mentioned, we can have a reasonable good context on them. And we can look at the photoluminescence and how photoluminescence change with change of carrier density or change of electric field, since we have 2 gates on top and bottom. what we see first in photoluminescence is this X naught is what I call the direct exciton, the charge neutral exciton. It's just an electron hole pair bound. But then once we start doping the sample, either towards N or P type, we have what is called trions. I mean, maybe Falco won't like that when I say trions or polarons. But we have now a charged exciton because we're adding electrons or holes into the system, and now it's like a 3-particle picture. And they get reducing energy because of this screening effect, because we're adding more and more of these electrons or holes. However, when we do electric field dependence, because this is a truly 2-dimensional material, there is no dipole moment to change energy. So there is no, we don't see at least a Stark shift effect. We don't see a change in energy. But we still see this direct exciton, the trion. Unfortunately for tungsten and selenide, there is these surface-bound peaks, which are usually related to disorder in the sample. Okay, this is some data that it was taken in collaboration. All this work is taken in collaboration with the Park and Looking group that I will acknowledge at the end. So this data was taken by Joe Shaw. So he compared photoluminescence with absorption on tungsten diselenide on MOSE2. So I want to mention, as in the previous slide, like we have this neutral exciton. We have the trion, which is these ones that move with carrier density. In either on tungsten diselenide or on MOSE2, we always have them, and they always go to lower in energy with increase of carrier density. In absorption, we also see this neutral exciton and the charged exciton, but they move in different directions. And the reason is when it's usually blue shifting because of the Pauli exclusion principle, since in tungsten diselenide, the spin polarization for the lowest conduction band, lowest band conduction band is different than the spin in the upper conduction band compared to MOSE2. In MOSE2 is the same. So usually in MOSE2 we see mostly a blue shift compared to in tungsten diselenide you either see a blue shift or a red shift for the other side. All right. So what if we put them together, two materials? If we put MOS2 or MOSE2 in this case, and tungsten diselenide. So as I said, we can put them together. They have different alignments. They have different gaps. And at the end, we can create this kind of p-n junction, where this is a device example. So we have, let me explain it maybe better in the next slide, but we have different gates. So there is a heterostructure gate. This rectangle on the bottom is actually a bottom gate for the heterostructure. We have a top gate on the heterostructure. And we also have contact gates to make the contact more transparent, to make it ohmic. And we can apply current in each of the layers, either on tungsten diselenide, which is the p-type semiconductor, or in MOSE2, which is the n-type semiconductor. Right? If we do photoluminescence, we can do photoluminescence on tungsten diselenide or MOSE2. We see each of these individual excitons for each of the layers. And if we do, if we also take photoluminescence on the heterostructure, we now see a photoluminescence peak, but a lower energy. It's like now the recombination is not coming from each of the materials, but now it's coming from the recombination is now coming from the electron in MOSE2 and the hole on tungsten diselenide. Because of the alignment, they have a lower energy, and that's what we observe. It's around 1.3 electron volts. Most of there is very low recombination from each of the individual layers. Once we obtain the photoluminescence on the heterostructure, each of the layers don't give much of excitons. All right. So, but I want to mention here. So we put these two materials together, but the alignment between them is important. So that's why I have this question. Is twisting angle important? So in order to find out what is the alignment, or we have to align them in momentum space as well, what we do is we use a second harmonic generation microscope. It's all in CIS, it's in biophysics department. We use a laser at around 400 nanometers, and it's polarized in one direction. Let's say if we have a TMDC, as I mentioned, it's a hexagonal crystal with two different materials it's either MO and selenium, right, in each of the lattice points. So if we align it, let's say to the zigzag edge, we obtain no second harmonic generation because it's the same material all over. But if we align it, in this case 30 degrees, now in the armchair configuration, in the same in the same direction as the polarization of the laser. Now we see two different materials, selenium and molybdenum. And so by keeping the polarization of the laser fixed and rotating the sample, we can be able to find out where is the zigzag edge for each of these individual materials. And that's what we did here. We did on the MOSE2, on the tungsten selenide, and on the heterostructure. And they are all aligned. They all have a minimum near this arbitrary angle, respective to the fixed laser polarization. So this is a second harmonic generation image of the heterostructure. So where we can see tungsten selenide and MOSE2, probably it's a little bit dark here. And we find that the alignment is less than 2 degrees. That's where we obtain this, the previous data. That's where we obtain this photoluminescence from the heterostructure, where we can see a bright interlayer exciton. But let me show you some videos to show like how do we know that they are really close to 0 degrees. So when they go dark, we're rotating the sample. Both of the samples go dark, or they go bright at the same time. However, if we do it in another sample, we do the same angle dependence in a misaligned sample, we can see that one of the layers gets bright first, and then the other one gets bright. So this is because of the misalignment in between the layers. And of course, in this layer, we didn't obtain any interlayer excitons. So we mostly obtain it once they are aligned in momentum. All right. I will show you that. Yeah, we will study the dynamics soon. All right. So this is the same device image, the one that shows us the interlayer exciton. As I say, we have tungsten selenide and MOSE2 across, forming this kind of 0 degrees. We are using the minimum of the conduction band in MOSE2 and the maximum of the valence band on tungsten selenide to form this interlayer exciton. So at the end, it's like a new semiconductor with smaller gap. That's how we see this heterostructure, right? Now we can measure what is the lifetime. So we have gates that we haven't used them yet, but we can measure the lifetime. So once we create them, how long it takes for them to recombine in the same spot of the laser generation. So we find for this sample, it takes around 260 nanoseconds to recombine. So as I mentioned before, in a single layer two-dimensional TMDC, actually, the lifetime of an exciton is around 2 picoseconds. So we have increased the lifetime by 5 orders of magnitude, right? So compared to what is on a single layer. Now if we start using the gates, so we have a top and a bottom gate, so we can start doping. We can using a configuration which we dope the samples. We can use the same gate. I mean, they have different thicknesses, but we assume by now that they have the same thickness. And we use the same gates, the same polarity. So we can dope the samples. We can dope one sample. I mean, if we use positive gate or if we use negative gate, we can be doping one or the other. And what we end up doing is we're shifting the energy of the interlayer exciton, but it's not really shifting much. It's by 30 millieVs. Okay, and it's always blue shifting when we add this carrier density onto the sample. So as I say, probably this is also due to screening. But there is not much of the shift on the peak position. But the lifetime gets dramatically reduced. So the lifetime goes from 250 nanoseconds at 0 gate to close to 10 nanoseconds once we dope the samples together, right? There is no electric field, so we make sure that we are not applying electric field across the sample. So it's all just pure, it's just mainly doping the layers. Okay, and then now I want to show absorption. That's what at the beginning I was talking about absorption in each of these layers. So if we do absorption measurements, which is a reflection measurement, we can see like there is a reflection peak for MOSE2 and another reflection peak for tungsten diselenide. So usually these peaks are for the neutral density, neutral exciton in each of the layers. So, but what we see is like once we start doping, once we start applying a positive voltage, this neutral exciton disappear. As what I mentioned before, as what I showed before for us, individual layers, once you start doping them, you start having trions, and therefore the absorption from the neutral exciton disappear. So what we have here is like under these conditions we are doping MOSE2 while tungsten selenide is still undoped. Or if we go now to a negative voltage regime, we are MOSI2 is still undoped, while we are doping tungsten diselenide to a more p-type material, right? So, but we only have a small window where the two of the samples are intrinsic. So that's why we believe like this small window for lifetime is still long when the samples are intrinsic. But once we start doping them, the lifetime reduces a lot. All right. Well, this is the explanation I just gave. But now if we use a different gate configuration, if we use one of them positive and the other one negative, now in an electric field configuration, so since this is an electron separated to a hole, right, they are in different materials, now we can use an electric field to make them closer or to like just stretch them, right? So, and that's what we did here. So using electric field, this is the displacement field, we can change the energy of the interlayer excitons by more than 200 millieVs. So this is a large change. Even in gallium arsenide, you cannot apply much electric field because, as I say, the binding energy is small, so you start ripping them apart. But the binding energy in these interlayer excitons is large. For the interlayer excitons, the binding energy is around 150 millieVs, so you still can apply more electric field to keep changing the energy, right? But also we see like the intensity changes with the electric field, and I will show here like the lifetime also changed. So for zero displacement field, the lifetime is around 250 nanoseconds, but we can increase it up to around 500 nanoseconds. We're kind of doubling the lifetime of these interlayer excitons with electric field. And as I mentioned, it's like a positive electric field is like we're stretching the separation between the electron and hole pair. I forgot to mention here, but the slope of this line of the energy versus displacement field give us a dipole moment of around 0.6 nanometers, and actually that's the separation between MO and selenium. I mean the metal of these two indices, which is mainly where the wave function is present. Right. Okay. While if we look at absorption now on the heterostructure, we still can see that MOSI2 and the tungsten diselenide absorption. So we haven't doped the sample. The sample is still intrinsic. So the Fermi level is in the center. What we are doing with this electric field configuration is just, as I mentioned, just stretching this dipole moment. All right. So now what Professor Westerveld asked me, right? So are they mobile? Can we see them moving? So what we did is then, this is the diagram of the contour of the sample. So the sample is like 20 microns by 10 micrometers. We shine a continuous wave laser on the center. So we are just collecting everywhere from the sample, but we are shining only in one spot at low power. This is 0.5 microwatts. So if we keep increasing power, the spot is hasn't changed much. But if we keep doing this process, like for example now at 100 microwatts, we are collecting from a large area, and we are seeing like now the spot looks like bigger on this region. And if we keep increasing power around 1 milliwatt, now it's hard to see here, but the whole sample gets illuminated. So we are generating interlayer excitons in the center, but because they are dipoles, they repel each other once you keep adding them with higher power. And at the end, what they do is they move. They are mobile. They have long lifetime, so they can go to different parts of the sample, even where we are not shining, even like 10 micrometers away. That there is no, we are not directly shining a laser on them, right? So we can get interlayer excitons even farther apart. All right. As I say, we are collecting from different spaces while fixing the excitation. All right. So now let's do the same. This is the same sample, right? So at the high power, if we this is all low temperature. Now we can do we can collect in a line cut. So we can collect in different positions of this line cut while still exciting in the same position. What we can do is now we can also look at the time dependent. We can find out how long it takes for an interlayer exciton to arrive in a certain distance away from the excitation spot, and that's what we did here. So on the excitation spot, we can see like the laser is this red red plot, right? So laser is on or laser is off. While the collection on the same spot for the interlayer exciton, it takes some time to get into the peak right after the laser gets on. and it takes longer for it to die after the excitation is off, right? So this is this long lifetime. But if we go 1 micrometer away from the excitation, well, first it's like the intensity is lower, right? Because it's not, now it has to move in space. It takes longer for it to reach a maximum compared to what it took for the on the laser spot. And if we go even farther away, it takes even much longer for it to reach the same maximum, right? To reach the same peak of intensity. So with these line cuts of time-dependent photoluminescence, we can now construct construct how long it takes per each of these points away from the excitation spot, and we can measure the diffusion constant. That's what I will mention in this next in the next slide. Right. So here's the same map, right? A high power. So these excitons, they are repulsive. They diffuse because of this column interaction. And if we do this is a line cut, the same line cut across the whole sample. Now we have a line cut for space, that's this X position, and we also have the y-axis is time, right? So we can find out how long it takes depending on where we are collecting from. And we see these kind of spikes, these lines on here, and also this is on the rising edge, right, when the laser turns on, and it is on the falling edge, so the laser gets off around 1 microsecond, and this is just how long it takes to recombine. So these spikes, well, we believe they are like interlayer exciton traps. So we see actually in the PL map we can see like there are some areas that are brighter than others. So they might be like some variations of the band gap on the sample, local variations on the band gap. So that's why they could be acting as interlayer exciton traps. So if we fit, this is still work in progress, but if we fit how long it takes per a given intensity in space, we can measure a diffusion constant of these interlayer excitons. We obtain around 3 centimeters per second. Mobility, we know the mobility of them based on the transport measurements. So we can assume that the electron and hole, the interlayer exciton mobility at the end will be similar as the electron and hole mobility, right? But these inhomogeneities they become like they are like exciton traps on the sample, right? But if we apply a current on one of the layers, like let's say if we apply a large current on tungsten diselenide, and we look at the falling edge, we end up seeing like these traps, they get reduced in intensity and also on how long they live. So applying current on one of the layers can be doing like a Coulomb drag, exciton drag, since we're tilting the potential on the plane, right? On the plane of tungsten diselenide, so might be that voltage that we're applying on tungsten diselenide might be helping to get rid of these exciton traps, right? Or these inhomogeneities.
What's the density approximate that cost again?
For the interlayer excitons?
Yeah, when you put the laser on, what typically
Okay, so let me go in a couple of slides I will say, but I can tell you right now that it's from our calculation, it's around 310 to the 11 centimeter square per centimeter square, right? So, but also bear in mind that these are p-n junctions, right? So these are a material that is mostly holes or electrons. So we can apply current across this p-n junction. This is a color plot of the current versus gates versus top and bottom gate. If we apply current on this p-n junction, we can also obtain electroluminescence. So we can get light out of, this is like an LED at the end, right? So we can get light out of these p-n junctions. Depending on where we place the gates, the top and bottom gate, we can get light out on this edge, or this is the side edge, the left edge, or the top edge, or even onto most of the recombination happens in this corner, but we can also get recombination on the center. So depending on how we dope the heterostructure. So this is, it goes from 1, 2, and 3. This is also the configuration for the gates, right? So we're either doping mostly tungsten diselenide, we're either doping mostly MOSE2, or we are kind of an intrinsic region. right? And so we can control where the recombination comes from spatially. But also, let me show you a video for that. So we can now tune the gates in this configuration in the, where the yellow arrow goes. And we can see in time how this the recombination center change over time when we're changing this gate configuration, right? So we can control that as well. If we just fix into one, if we just park the collection into one spot, for example, either in the center or one of the edge, we can change the bias voltage configuration. So we see once we start applying like a few micro amps, then we start seeing the interlayer exciton, and also it's shifted, right? It shifts with more application of voltage bias. And if we apply an electric field, we also obtain the same plot that, as I mentioned, when there was no current applied. There is no light applied here, right? So this is all just generation because we're applying current on this PN junction. So, and we obtain a similar slope, so where the dipole moment is around 0.6. I mean, saying that we can generate these interlayer excitons electrically, right? So there is no application of light here. And if we measure the lifetime of this electroluminescence exciton, right? I mean, it's a tunable interlayer exciton. The lifetime is also long. It's around 150 nanoseconds. So we can generate them electrically. So we can use them to, we can tune the energy with the control that we have with the top and bottom gates. And we can control where they come from, where is the emission from. Okay, so if we do a power dependent, now we're collecting from the same spot as the excitation. So if we do a power dependence of PL, what we observe is actually the peak position in energy for the interlayer exciton shift with power. So the shift is around, at least for this spot and for this laser power, we obtain a shift of around 10 millielectron volts. If we assume like they are a parallel plate capacitor, and based on this blue shift with power, we can roughly estimate the interlayer exciton density. And the interlayer exciton density is around 10 to the 10. So Professor Westerveld asked me. There is this theory paper where they claim like interlayer exciton, they give an interlayer exciton phase diagram on TMDCs, and they claim like since the binding energy is large, we could probably obtain Bose-Einstein condensates on interlayer on TMDCs, right? At larger temperature than in gallium arsenide, mainly because of the binding energy is large, so we can push them to higher temperatures. So they give like what will be like the BKT temperature for this VC, right? This is the degenerated exciton gas. So so far, I mean, we're around here. So, but still, we need to do more experiments to see if we can obtain any of these condensates, right? All right, let me now switch gears. So, as I mentioned, we in a single layer we have these excitons and trions, right? The charged excitons. So, if we can make quantum dots out of it, where we can confine either electrons or holes, and generate excitons in those I mean, confined areas, we can at the end produce like single or few trions. We can just produce few of them, right? And this is what we have done with quantum dots with in collaboration with K, and this is all in collaboration with the Park and the Looking group. So we have made quantum dots that they are on a single layer, so we can optically drive them. We can optically look at PL. This is the PL from the quantum dot area. We see the neutral exciton. We also see the charged exciton. But there is two peaks. There is a big peak that will be the delocalized trion peak. And then there is this small peak, which is like a localized trion peak. So we have this is our local gates, so we can control the carrier density in parts of the MOSC2 while keeping these ungated regions that they are only controlled by the bottom gate. So we can deplete or accumulate in these spots, right, in space, and we can see that this localized spot gets brighter or dimmer depending on where we put the gates, where we gate the sample. So these are these confined induced features. This is something you cannot do that easily in gallium arsenide, at least not gate control, because of the binding energy again. So the binding energy on a single layer is, for the trion, is around 30 millieVs compared to just few millieVs on a trion in gallium arsenide. Okay, so we can make this gate control localized trions, right? So this is another example of, this is a PL map as well. So we are looking at the emission from this region where we have this is like a quantum dot region, right? So we can control the gates to make it brighter or dimmer, depending on where we place if we do either accumulation or depletion on these local gates, right? So, and also since they are lines, we can have like a 1D confinement. So you see we are depleting this region, we're getting rid of trions in this region, while there is mostly trions on the ungated line in the sample, right? And it's mostly trion emission from that line. Okay, but then this is another part. Like we can also couple we can couple TMDCs to other materials, or we can also couple them to plasma polaritons. Like we can couple them to silver. And plasma polaritons have out-of-plane polarization. The electric field is in out-of-plane polarization. So if we can look at the spectra at a PL, so we are exciting PL in this spot, and we can also collect in the same spot. That's far field. This is the blue spectra, where we can obtain the neutral exciton and the trion. But if now we collect away on this grading, away from the excitation spot, we can also obtain PL. But now there is an extra peak. This is the XD, which is a dark exciton. So the dark excitons in TMDCs have an out-of-plane polarization that you cannot observe them in far field. As you see, the blue plot is there is no peak here. But once you couple them to plasma polaritons, like silver, right? Like we can now excite this out-of-plane exciton. I mean, we can now collect them. We can now see them. This dark exciton, right? This is all in collaboration with the Park and the Looking group. In gate dependence, you also can, I mean, this is silver, so you can use silver to gate as well. You can gate the sample, and you can compare the PL map of gate-dependent PL map on the far field collection, or also on the surface plasma polariton. I mean, outside, right, on the grading, and you can see like the dark exciton is bright on this region, right, when we're collecting from the plasma polarity, from the SPPs. Right, so this can also be useful for like plasmonic optical modulators or switches, since we can use this silver to either excite this dark exciton or not, right, with the gate on the bottom. Well, let me skip this. There is only 9 minutes. We also can, this is in collaboration with the capacitor group. We can also use plasma polaritons, I mean silver, again, to find out. I mean, in the capacitor group, they use near field. They can collect from near field, right? So they can collect directly on the sample and not being limited by the diffraction limited spot. So they can collect on the sample, and they can, if we are shining, in this case, we're shining a laser of a given wavelength, we can look at these ripples. There are ripples on each of the samples. This is a triangular circular sample, and they can look at the wavelength. I mean, in plane, or from this when they are collecting using this like optical fiber be moving across the sample, and they can look at what is now the wavelength on the sample, and based on the difference from what you are exciting with and what you are collecting from, you can obtain the refractive index of boron nitride. Either this is in plane, or if you use surface plasma polariton like silver, you can also obtain out of plane, because as I mentioned, the SPP has an out of plane electric field. So in collaboration with the capacitor group, we have obtained what is the refractive index for boron nitride in plane and out of plane with some precision, right? So it's all based on this on the change of the refractive index on the material. We can also use them to engineer different resonators. So like this is a whispering gathering mode resonator that we made with Michelle, right? So we can just excite on this region, and we can collect across the sample, and you can see like most of the light gets guided onto this edge. So this is like a whispering gathering mode resonator. Even we can make different fancy forms, shapes, like a star. So this star has these gratings on each of the tips. We can excite in one of the gratings on the tips, and we can collect in other. We can collect light directly on other places on the sample, and we can see like the tips get. Most of the light comes out from these gratings on the tip as well. Hard to see from this screen, right? Actually it's better here. So where we can see the light is coming out from these gratings. So we can guide light using boron nitride, using a few layers, right, of boron nitride. Well, now let me go to future directions. So mainly for the interlayer exciton part. So we can make now a Coulomb drag experiment with interlayer excitons. So we can apply current in one layer and measure the voltage in the other layer. So that's the next generation of devices that we have. We can increase the lifetime of the interlayer exciton by placing an insulator in between. That's what we're also working on, by placing boron nitride in between these TMDC materials. We can also couple surface plasma polaritons on silver to heterostructure to look at what is the, maybe we can be able to see now the dark interlayer exciton, which also has an out-of-plane component. We're also looking to, if we want to see the large diffusion on these samples, we're looking for also making bigger samples. So we can now make exfoliated heterostructures with have sizes of around 100 micrometers. So the exfoliation process here is different. It's a little bit more dirty, but we can obtain, we have measured one of these structures, and we obtain interlayer excitons. It's a little bit more it's broader, but we still can obtain it in these kind of large size heterostructures. All right, so this is the summary and the outlooks, right? So we have high quality TMDCs monolayers. We can do transport on them. We can also look at PL and how sharp they are. Also the demonstration of this confinement on TMDCs. We can control trions and excitons with gates. We can get rid of the excitons and mostly see trions from each of the individual layers. We also have the interlayer exciton optoelectronics. We can have like a whole device diffusive interlayer exciton transport. We also have seen this gate confinement of trions in TMDCs that is something you cannot do in gallium arsenide or other competitors, right, for other three-dimensional semiconductors, right? This is part of the outlook that I mentioned before about the interlayer excitons. So let me acknowledge the Kim lab, right? Kate, Andy, Ke, Ishan, and others. There was no space. The Park lab, Hong Kong, Giovanni, Joe, Alex, Christian, and Andre, sorry. Also, they are kind of between the Misha's lab and Hong Kong lab, right? And theory, we have had support from Dominic, Shang, Falco is also here, and Richard, and Eugene Demler. And the Capasso group from Professor Capasso, Antonio, Kundan, and Michelle. And from the contact part is that most of the work was also done in collaboration with Jim Hong at Columbia and Alex Shui, and of course the boron nitride providers. Okay, thank you.
Comments? Yep.
Yeah, so for your interlayer exciton work, so you had a double layer structures where you had, selenide and disulfide or whichever one it was. Is it realistic to have interlayer excitons where you have a double layer of the same material with like a huge electric field applied?
It's possible, yes. Yeah.
And would that have any like different properties? Or?
I mean, as you say, you have to apply electric field there. Right? You have to create the band misalignment too.
Yeah, like you have thick layers, so maybe the voltage isn't realistic.
No, it's possible. I think, yeah, it's possible. Yes.
How does it react to strain? With the excitons, does the energy go down with straining it, or what?
So you just strain the sample?
Well, suppose you took a tip and you made a dimple into the material. And do the excitons like that, or they don't like that? Or?
If you you strain it, then that's a good
Just
question.
think the old days we took actually mounted a piece of germanium with a screw, and it turned out all the excitons love to be right there. I mean,
Yeah, I mean, if the gap gets lower, then they will love to be there, right? So, but I don't know if it's strain. Let me actually. Energy will get higher. In TMDCs, the energy will get higher. If you, I mean, when you cool down, also there is a shifting energy. It gets higher when you cool down, so it's similar to a strain, right? So.
but well,
Right,
it's
right.
complicated because it's right.
Yeah.
Do you expect a limit on the number of layers of the insulator you can
Yes.
put between the
Right. Yeah. So I just mentioned that putting between, I mean, insulator in between could help to increase the lifetime, right? But that will reduce the binding energy as well. So there are calculations that up to 5 layers, it should be possible to have a reasonable, like I think, few milli electron volts of binding energy. But that's going to reduce.
the increased lifetime?
Yeah, it will increase lifetime dramatically.
When you said 500 nanoseconds, are you measuring the lifetime directly, or?
Yeah. So we're doing time-dependent photoluminescence.
Microsecond pulse laser, or do you have a faster one on?
We have a we pulse a diode laser with 100 kilohertz pulsing, so that's where we still can obtain this long lifetime.
So maybe I missed it, but as far as like getting towards exciton condensate, do you think it's more about like trying to get longer lifetimes, or just pumping harder with the laser, or?
I think pumping harder maybe has another problem, right? Which is heating the sample. So what we're thinking is we have to get rid of first of these inhomogeneities. So we're still trying to understand what are these inhomogeneities to start with. So they are not correlated to bubbles on the sample. So they are something to do with like reduction of gap or so onto the sample. So we have to get rid of them first, or understand them how to get rid of them.
Yeah, along those same lines, I mean, do you see kind of electric trapping due to the fact that the barriers themselves are polar? Like you have these thick boron nitride layers, right? They're polar themselves, right? And the question is how defect-free is that? I mean, are they real clean single crystals, or?
Boron nitride is full of, yes.
Yeah, so I'm just wondering whether or not you're getting localized kind of
But
polarized.
certainly that if you see that the PR map, there is some localized products. So we don't know where it comes from. Potentially some residual disorder in boron nitride, but supposedly boron nitride it's a near perfect crystal set. So yeah.
If there is a suspect, I guess it's mostly the TMDC, because there are defects on the TMDCs.
Yeah, but I'm wondering if you have kind of polarization noise in the boron nitride, that's going to look like a dirty barrier, right?
Mm-hmm.
So I was interested in this. That if you apply a field, out-of-plane field, you increase the lifetime dramatically.
So we only
500 is 500 nanoseconds.
Right.
So did you? I don't know. Did you do any other experiments on that? Like, can you do this in the doped regime, or?
When you apply electric field in a doped regime?
Yes. Like have a field, have this similar field, but not in the gap, like basically.
We haven't tried that because once we dope a little bit, then dramatically the lifetime goes down. But
right, but if the field increases it again, it might still be in it because you can see different effects in doped regime.
yeah, we haven't tried it. Probably that's really good. Yeah.
Right? Any other questions? Okay, if not, let's thank the speaker.